Hello everyone, welcome to Digital Communication Tutorials. In this video, I'm going to discuss on the topic delta modulation. Before I begin the discussion on delta modulation, I would like to inform you that delta modulation is in fact a modification to differential pulse code modulation. I have already created a video on differential pulse code modulation, so I would highly suggest you to watch that video first before you continue with delta modulation. If you already have watched that video, let us start with the discussion on delta modulation. In our previous discussion, that is on differential pulse code modulation, we have learned that correlation between adjacent samples can be used as an advantage to reduce the overall bit rate as well as the number of bits required to transmit a sample. As an example, consider the diagram shown in figure 1 here. The neighboring samples are differentiated only by a small change in their code words. So, when this is the case, we already have stated that the neighboring samples are going to exhibit a lot of correlation. We should note that sampling an analog signal at a rate much higher than the Nyquist rate, that is Fs greater than 2W, will create a sampled signal that will have its samples very closely spaced. So, we will obtain an output waveform which looks pretty similar to what we have here. Now, we have already established in our previous discussion on DPCM that closely spaced samples will exhibit high correlation. So, if we intentionally sample the input baseband signal at a rate much higher than the Nyquist rate, that is Fs greater than 2W, then the sampled signal created will have a very high correlation between any two adjacent samples. This also means that the amplitudes vary by a minimum value. In order to explain that, let me come back to the waveform here. You see, this is in fact a waveform for PCM. Here, the first sample amplitude is 0, 1, 0, whereas the second sample amplitude is 1, 0, 0. So, the difference between them is not a 1-bit increment nor a decrement. However, if I intentionally sample the input signal at a rate Fs much greater than 2W, then the sampled signal created will have only 1-bit variation between any two samples, and that in fact is what the overall idea behind delta modulation. Now, when we have only 1-bit variation between any two samples, then it is possible to simplify the quantizer to the one that has only two representation levels than L representation levels as seen in either DPCM or in the PCM technique. So, the modifications that are required to convert a DPCM system into a delta modulator are given by: first one is intentionally sampling the baseband signal at a rate Fs much greater than the Nyquist rate, that is 2W. This will create very high correlation between adjacent samples. Second, instead of using an n-bit quantizer, the delta modulator uses a 1-bit or simply 2-level quantizer. We say it is 2-level because when I say 1 bit, it is 2 to the power of 1, which is 2 representation levels. So that is why this is also called as a 2-level quantizer. When I incorporate these modifications to the DPCM will simply convert to delta modulator. So, in simple words, we can say the delta modulation is simply a 1-bit version of the DPCM. Coming back to the waveform here, we see the sample amplitudes of the first and second sample vary by a value which is greater than the step size of the quantizer. In fact, when we were discussing the derivation for signal to quantization noise ratio of both the mid-riser as well as mid-thread quantizer, there we mentioned that it is possible to have an amplitude variation from -4 sigma x to +4 sigma x, where the sigma x in fact represents the standard deviation of the input signal. This means that any two sample amplitudes will have a difference greater than the step size delta. This is the reason why we use an n-bit quantizer in both PCM as well as DPCM. However, in delta modulation, the neighboring sample amplitudes are allowed to vary only between plus or minus 1 delta, where delta, once again here, is the step size of the delta modulator. Please note this should not be confused with the capital delta, which was the step size for both the PCM as well as DPCM. We will relate the step size of the PCM as well as that of the delta modulator in the later part of the discussion. So, when we apply delta modulator on the input signal, it provides a staircase approximation to the oversampled version of the input signal as shown in the diagram here. Please note the difference between the input and the staircase approximation is quantized into only two levels, which are plus or minus delta. Talking about this diagram here, you can see we have a continuously varying signal which is x of t, and then we have the staircase approximation, and this is represented as u of t. Now the staircase approximation is because of the 1-bit quantizer. Now let us learn how a staircase approximation is generated by the 1-bit quantizer. To do this, we identify the threads, and the right side edge of the thread is identified as the sampling instant. So when we perform the quantization at the instant of sampling, if the approximation falls below the signal at any sampling instant, then the approximation is increased by delta. If on the other hand, the approximation lies above the signal, then the approximation is decreased by the value of delta. Now when I say delta, it is small delta always. Let us now learn how it is done. Let us start with this thread here. This is the horizontal line, which is the thread. Now at the sampling instant, which is this vertical line, and when I take the thread edge, I see the input signal is actually lying below the sampling instant. So now I have to decrease the approximation by a value of delta. That is why now I have to draw a line coming down. Now we will have one more thread. Again, at the edge of this thread, we identify whether the signal is lying above the sampling instant or below. In this case, you can see it is lying below. So once again, I'm supposed to draw a line coming down. Followed by that, we once again have a thread. At this instant, you will note that the input signal lies above the approximation. So I have to now draw a line going up by a value of delta. So this is how you are going to create the approximation, particularly the staircase approximation of the input signal x of t. I am going to repeat once again. If the approximation falls below the signal at any sampling instant, then the approximation is increased by delta. If on the other hand, approximation lies above the signal, then the approximation is decreased by delta. Since our input signal is oversampled, we find that the neighboring samples exhibit high correlation. Therefore, we find that the staircase approximation always remains within the plus or minus delta of the input signal. This is the reason why we in fact intentionally oversample the input signal. If the staircase approximation always remains within plus or minus delta, in simple words we can also say it as the quantizer being not overloaded. I repeat, not overloaded. Let us talk about the step size of the delta modulator. As you can see from the diagram here, delta denotes the absolute value of the two representation levels of the 1-bit quantizer. The two levels of the 1-bit quantizer which are used in the delta modulator are itself indicated in the diagram here. Please note this is a transfer characteristic, and we in fact have used a mid-riser quantizer. And since we only have two representation levels, we have only two threads here and one riser. Now since it is a mid-riser, the origin must lie in the middle of the riser, and the overall step size has to be capital delta. Since in our discussion we have taken the variation to be only plus or minus delta, this representation level is said to be plus delta and this is supposed to be minus delta. So the step size capital delta of the quantizer is related to the small delta as delta is equals to this amplitude minus of this amplitude, which is delta minus of minus delta, which is 2 delta. So from this equation we note that the step size of the PCM as well as DPCM is equal to 2 times the step size of the delta modulator. Right, with a brief introduction on delta modulation, let us start the discussion on the delta modulator transmitter. Please note, the delta modulator transmitter is directly derived from the DPCM system. In fact, if you look at the diagram very carefully here, we had in our DPCM system a n-bit quantizer and in delta modulator it is replaced by a 1-bit quantizer. Here we had a predictor in the DPCM, whereas in delta modulation the predictor is replaced by a 1-bit delay element. This is still a predictor, but now the predictor is simplified as a 1-bit delay element. Let the input signal be denoted as x of t and the staircase approximation be denoted as u of t. We already have given that here. So the continuous time varying signal is x of t and the staircase approximation is u of t. So I can now say the transmitter consists of a summer, a 2-level or a 1-bit quantizer, and lastly an accumulator. So this block with discontinuous lines is the accumulator. The sampled input x of NTS is said to be unquantized version of the input signal, whereas x cap of NTS is the output of the accumulator, or we can also call it as an approximation of the input signal. So the input to the quantizer, which is E of NTS, is the prediction error that represents the difference between the present sample value x of NTS of the input signal and its latest approximation, which is x cap of NTS. Now I can relate these terms in terms of an equation as E of NTS is equals to x of NTS minus x cap of NTS. Coming back, as I already said, the predictor here is nothing but a 1-bit delay element. So the output of the predictor can be written as the input of the predictor delayed by 1-bit interval. This in fact is given by the equation format here as x cap of NTS, which is the output of the predictor, is equal to, look back, input of the predictor is u of NTS and there is a 1-bit delay here. So I can write it as u of NTS minus TS. Now substitute equation 3 back into equation 2 in the place of x cap of NTS, which will give us a new equation for E of NTS as x of NTS minus u of NTS minus TS. Once again, coming back to the diagram, now let us write an equation for the output of the quantizer. Now we note that the input of the quantizer is the prediction error, which is E of NTS, and the output of the quantizer, which is denoted as B of NTS, can be written as delta into sine of E of NTS. This is a very important notation, where B of NTS can be said to be the algebraic sign of the error signal and delta is the scaling factor. Let us go back to the transmitter and verify this. You see the input to the quantizer is an error signal, and since we only have a 1-bit quantizer, the output of the quantizer will definitely be the input plus or minus 1. So instead of having either a digit or a number at the output of the quantizer output is represented as the sign of the quantizer input, which is E of NTS. That is why we have written it as delta into sine of the input of the quantizer. So from equation 5, we note that the output of the quantizer is a 1-bit word, which is denoted by B of NTS. This is mainly because the quantizer is a 1-bit quantizer. Let us now move on and discuss on the predictor input. Now you can see the predictor input is given as U of NTS. Now I can write U of NTS as B of NTS plus x cap of NTS, right? So I have written this in the equation form here, x cap of NTS plus B of NTS. We know that x cap of NTS is the output of the 1-bit delay element. So I can write it as U of NTS minus TS plus B of NTS. This is another way of representing the predictor input. To understand more about how the delta modulator works, let us for time being assume accumulator is initially set to 0. That is, x cap of NTS is set to 0. We will substitute this into equation 6, which is rewritten here. U of NTS, which is accumulator input, is equals to x cap of NTS, which is accumulator output, plus B of NTS, which is the quantizer output. Now since x cap of NTS is 0, we will place it with a 0, and B of NTS is taken from equation 5, which is delta into sine of E of NTS. Now I can write delta into sine of E of NTS as delta into summation I varying from 1 to n sine of E ITS. Now this I can write also as summation I varying from 1 to n B of ITS. Therefore, by looking into equation 7, we can conclude that at each sampling instant, the accumulator increments the approximation to the input signal by a value plus or minus delta depending on the binary output of the modulator. Please note, this is the binary output of the modulator. So we can understand this as, if the output of the quantizer is plus, then the accumulator increments the approximation by a value of plus delta. On the other hand, if the output of the quantizer is minus, then the accumulator decrements the approximation by the value of delta. This is how you are going to get the staircase approximation of the input signal. Right. So that is about the discussion on the transmitter part. Let us now move on to the receiver part. Figure 5 here shows the delta modulation receiver. In the absence of channel noise, we assume the output of the transmitter and the input of the receiver are the same, which is B of NTS. In the receiver, the staircase approximation U of NTS is reconstructed by passing the incoming sequence B of NTS through an accumulator in a very similar fashion as what is being done at the transmitter. So we have an accumulator here which in fact works very similar to the accumulator at the transmitter. So the output of the accumulator is once again X cap of NTS. So when I add the received signal, which is B of NTS, with the output of the accumulator, which is X cap of NTS, this addition will create the staircase approximation U of NTS. You can come back and see equation 6 here. X cap of NTS, which is the accumulator output, plus B of NTS is nothing but U of NTS. So that is what we are doing at the receiver as well. B of NTS plus X cap of NTS is U of NTS. Lastly, the out of band quantization noise in the high frequency staircase waveform, which is U of NTS, is eliminated by passing it through a low pass filter with a bandwidth equal to the original signal bandwidth. This in fact will convert the discrete time signal U of NTS into the continuous time signal U of T. Coming back to the equation 8 here, we note that in a delta modulation system, the receiver reconstructs the transmitted sample by simply adding the sign of the prediction error to the previously reconstructed sample. That is, if the sign is plus, then the previously reconstructed sample is incremented by delta. On the other hand, if the sign is minus, then the previously reconstructed sample is decremented by delta. This is how a delta modulator works. By comparing the differential pulse code modulation and the delta modulation receiver diagrams, we will see that except for an output low pass filter, the delta modulation in fact can be considered as a special case of differential pulse code modulation. You should note, delta modulation particularly offers two unique features compared to DPCM. The first one is the use of the 1-bit code word for the output. This eliminates the need for code word framing. The second unique feature is the simplicity of design for both the transmitter as well as the receiver. These two features make the use of delta modulation attractive for some types of signal communications and for digital voice storage. Right, with that we come to the end of this discussion on delta modulator. I hope you liked this video. If you did, kindly press that like button and subscribe to my channel for more videos on digital communication. Thank you for watching. Have a good day.